Hello everyone. Today's presentation focuses on analyzing environmental factors that drive wildfire spread risks using machine learning techniques. Many Indigenous communities, particularly remote First Nation regions across Canada, are disproportionately affected by wildfire risks due to geographic isolation, limited initial response resources, and shifting climate patterns. When a wildfire spreads rapidly, critical evacuation routes and community infrastructure become vulnerable very quickly. The central research question asks, how can cluster analysis of environmental weather variables help identify distinct wildfire spread risk profiles to improve early warning and response strategies for vulnerable communities? The objective of this project is to model environmental conditions to predict high-risk fire spread scenarios. Proactive, data-driven insights allow communities to transition from reactive emergency response to predictive risk management, helping safeguard community lands, culture, and life. To address this question, the Canadian Fire Spread Dataset was utilized, focusing on key daily weather observations. 4 primary variables were selected for clustering: maximum temperature, Tmax, which dictates the dryness and ambient thermal intensities. Relative humidity, RH, directly influences moisture retention. Wind speed, WS, is the primary driver of fire acceleration and the rate of spread. Daily precipitation, PREC, represents natural suppression and moisture inputs. These 4 variables were chosen because together they cover all the main physical drivers of wildfire behavior. Temperature and relative humidity determines how dry the trees, grass, and forest floor become, making fire easier to be ignited. Wind speed supplies oxygen to the flames and physically pushes the fire forward, controlling how fast it spreads. Precipitation acts as a natural dampener that cools the ground and raises moisture levels. Combining these specific variables gives the K-means model the weather inputs it needs to separate low-risk days from dangerous fire-spreading conditions. For data processing, missing values were handled, skewed variables were log transformed, and all features were scaled using standard scaler. Standardizing these variables ensures that large numerical values like wind speed do not artificially overpower features with smaller numeric scales during calculations. First, looking at the correlation heat map, this chart shows how strongly our weather variables relate to one another. How to read it? Each square shows a number between -1 and +1. Bright or dark colors mean a strong relationship, while neutral colors mean little to no connection. This tells us that there is a strong negative correlation between temperature and relative humidity, meaning as temperature rises, humidity drops significantly, creating dry conditions. We also see that higher temperatures and lower humidity correlates directly with higher historical fire spread rates. This confirms that these weather variables move together in predictable ways during wildfire events. Next, moving to the box plots, these charts show how our data values are spread out across each weather metric and help us spot any unusual extreme weather days. The central box shows where the middle 50% of the daily data falls. The line inside is the median, and the dots outside the line whiskers represent extreme outlier days. So the box plot shows that while most summer days fall into a normal temperature and humidity range, there are distinct outlier days with unusually high wind speeds and spikes in temperature. Spotting these outliers is critical because severe wildfires don't happen on average weather days. They are triggered by these exact extreme weather spikes. Finally, looking at the bar charts, these visuals summarize the average values and overall distributions across our weather metrics. Each bar simply represents the average or total frequency of a specific variable across the data set. And what this tells us is that while the bar charts give us a clear baseline for what a typical weather looks like in this data set, they show that high-risk weather events are relatively rare compared to normal days, which highlights why we need a clustering model K-means to pull those rare high-risk days out of the background data. So, looking at the methodology, coding, and initial results. For the core methodology, the K-means clustering algorithm was implemented in Python using the scikit-learn library. As shown in the code snippet, The k-means algorithm was set up with k equals 3 clusters and a fixed random state for reproducible results. We then called .fit_predict on our scaled weather features x_scaled to compute the cluster centers and assign a cluster label to every daily record in our dataset. The scatter plot, here we are, the scatter plot models cleanly separates the data into 3 distinct groups with the block X markers highlighting the calculated cluster centroids. And then to interpret these clusters, the average weather conditions for each group were plotted on the bar chart. This makes the physical differences between the clusters immediately clear. Cluster 0, cool and wet, shows the lowest average temperatures, high relative humidity, and regular precipitation, translating to a low historical fire spread rate. Cluster 1, moderate risk, displays baseline summer temperatures and light winds corresponding to a moderate fire spread rate. In Cluster 2, extreme risk spikes sharply in maximum temperature and wind speed while dropping in relative humidity, isolating the exact condition where severe fire spreads occurs. Connecting these initial findings back to the core community problem, it was demonstrated that fire spread risk is not driven by high temperatures alone, but by specific compound conditions, particularly wind gusts combined with sharp drops in relative humidity. From a decision-making and planning perspective, these risk profiles can support Indigenous fire management teams in several key ways. Resource allocation, pre-positioning suppression equipment and personnel when 3 to 5 day weather forecasts align with Cluster 2 parameters. Community safety, establishing automated data-informed alert levels for emergency management officers before a fire starts spreading. So current progress and next steps. Thus far, data pre-processing, exploratory data analysis, and baseline k-means modeling have been completed. Moving forward, some examples of next steps could involve evaluating density-based algorithms to better capture irregular weather patterns, as well as integrating spatial mapping features to tailor these insights to specific local territories. Thank you very much for listening.